Welcome to Astronomy 103. In this segment, we will talk about the galaxy and other galaxies. A galaxy is a huge collection of stars that is isolated in space and held together by gravity. We happen to live in one such galaxy called the Milky Way galaxy or the galaxy with a capital G. The structure of the galaxy looks like something like this. There's a disk of stars. Within this stars there is a spiral arm, and the center of the galaxy is a bulge. So how do we know the galaxy actually looks like this? Well, one way we did this is by counting the number of stars in different directions. So William Herschel first did this in 1756, and he discovered the galaxy looks like a disk. Right? Note that the sun is the center of his disk. Now Herschel didn't have a way to measure distance, so he just assumed that stars are uniformly distributed. So the real revolution came when the next rung of distant ladder was discovered in variable stars. Okay, so let's review the distance ladder again. So the way distance ladder work is that we use measurements of nearby things, right, to find estimates to further things, and use those estimates to find estimates to yet further things. So we bootstrap our way up. So for instance, we use radar ranging to find distances to the nearest planets and basically establish what the astronomical unit is. From the astronomical unit, we can basically look at parallaxes for the closest stars, and the Hipparcos satellites extends the range of parallaxes to about 200 parsecs or so, or 700 light years. Right? These days, actually, there's another satellite called Gaia, which can actually pushes all the way to about a few kpc, a few kiloparsecs or so. Right? So, the parallax distance, for the most part, is very hard to measure, but now with these new satellites, we can actually measure it pretty well. So the measure distance starts beyond this, all right? One has to start to use something called standard candles, right? So objects whose luminosity is known. So for instance, if you know the luminosity or the brightness of a candle or light bulb or some star, you can find this distance by measuring its brightness that you observe. So the further away it is, the lower its apparent brightness, right? In particular, the energy is spread out over an area of a sphere, which is 4 pi r squared. And so as you move further away, r squared gets bigger and bigger, and so basically the energy per unit area gets smaller, or the lumina or the brightness gets smaller. Okay, so the first standard counts that we encountered were main sequence stars, right? So for instance, if you know where you are in the HR diagram, we tell you the luminosity of each spectral type. So to find this is the main sequence star, what you do is to figure out what the spectral type is. From that, you know what the luminosity is going to be. And then from its luminosity and its apparent brightness, you can figure out what the distance is going to be. So using main sequence stars as standard candles, we can basically see the stars anywhere in our galaxy. So we can basically see everything up to about 10 kiloparsecs away, or 10,000 parsecs away, or about 30,000 light years away. Okay, so that's one standard candle. Now there's another standard candle called variable stars, right? So it turns out that all stars oscillate. Okay, so oscillations are basically sound waves. So the entire star will vibrate because of sound waves inside of it, right? But the time it takes the star to oscillate or vibrate depends on the time it takes for sound to cross the star. So for instance, it's the same as a bell, basically. A bell oscillates and oscillates at a particular frequency. That frequency actually is determined by the time it takes sound waves in metal to cross the entire bell. All right, so for instance, larger bells oscillate more slowly because it takes more time for the sound waves to cross the larger bell than it takes a smaller bell. So large star, like large bells, oscillates more slowly than small stars. Right? It's not a universal thing. It just happens that it's true for bells. It's true for stars as well. Late in their evolution, all right, bright stars for a very short period of time have unusually large oscillations. So there are stars which take about 1 to 100 days to pulsate, and these are called Cepheid stars. Stars take less than 1 day are called RR Lyrae stars. Right? And stars take longer than 100 days to oscillate are called Mira variables. The ones we are concerned about is Cepheids. Right. So sometime in a star's evolution, all right, the oscillations can become unstable and grow enormously and change the brightness of the star really quite greatly. right? So for instance, this is a star called Mira, right? Named after the Mira variables. And you can see basically in one frame at the top is rather dim and small. The frame at the bottom is rather big and bright, right? So the variable star Mira basically at its dimmest and its brightest, right? Now, this is how Cepheid variables work. Basically, if you look at the star, it vibrates every now and then, right? And as it vibrates, it gets brighter. As it expands, it gets brighter. And as it contracts, it gets dimmer again. Okay. Now, large stars are brighter than small stars, right? So, and because large stars also tend to be brighter overall, there's going to be a relationship between the period that you measure, i.e. the time it takes per oscillation, and the luminosity of these oscillating stars. Stars with longer periods should be larger and brighter than stars with shorter periods. Right? The larger star is, the longer its period oscillation. So Henrietta Leavitt first showed this is true for Cepheid variables by looking at a set of variable stars and imaginary clouds in order to see the stars the same distance. So she looked at a bunch of stars in the imaginary cloud. All the imaginary clouds are basically at the same distance relative to Earth, and so basically she was able to show that they had different that the less bright stars had shorter periods of oscillation. So Henry Leavitt discovered the first periodic luminosity relation for Cepheids. And so this relation makes a Cepheid into a standard candle, right? So for instance, once you measure the period, you basically know how luminous this thing is, and by measuring apparent brightness on Earth, you can tell how far away that particular star is. All right, so there's Henrietta Leavitt, right? She's one of the first women astronomers. And she measured basically the period luminosity relation for variable stars with long periods, 1 to 6 days, which are called the Cepheids. Okay. All right, so this is basically the difference between a Cepheid and our Lowry star. Our Lowry star have periods about less than a day or so. Cepheids have much longer periods. All right. Leavitt was part of a group of women astronomers, which were back then called computers, that looked over many thousands of places, and including Annie Jump Cannon, who we encountered already at the Harvard College Observatory. All right, so basically these are all the women working, looking at photographic plates back in the day. All right, and here's her relationship. All right, there's the Cepheids. All right, there's the Aurelaries. The Aurelaries have pulsation periods less than a day or so. There's the pulsation period on the x-axis, the luminosity on the y-axis, and there's a relationship. It's actually pretty tight. So basically, if you can measure the period, you know exactly what the luminosity is going to be. All right. So you can basically do this now. Cepheid variable can use the standard count. So you figure out its period, its luminosity by measuring its period. So that's from the previous plot right here. And once you know the luminosity, divide by basically its apparent brightness, right, which you measure to get the distance, right, from the 1 over r squared formula. All right, so here's a quick summary again of the distance ladder. So you use radar bouncing to find distances to Mars and Venus, and so you figure out what 1 AU is. Once you know what 1 AU is, you use parallax to measure distances to stars within a few thousand light years. Once you know the distance to these stars, find the luminosity of the main sequence stars. Use the main sequence of standard candle to find the distance to stars throughout the galaxy. Once you know the distance to cluster stars in the galaxy, find the luminosity of Cepheid variables. All right, using Cepheid as standard candle, you could figure out the distance to galaxies outside the Milky Way. So this is really critical. The Cepheids are the key that allows you to look at measure distances for galaxies outside the Milky Way. All right, so there's our little distance ladder again. Radar, stellar parallax, spectroscopic parallax. This is the main sequence stars, using them as distance ladder. And then there's variable stars at the top. And by this point, basically, we've gone from 1 AU to 200 parsecs to 10,000 parsecs, and now we're out at megaparsecs. We're out in intergalactic space. Okay. So, for now, we'll focus on the Milky Way. So, we're going to look at something less than, let's say, 10 kiloparsecs or so, or 30,000 light years. So, once we know the variable stars as standard candles, right, the size of the Milky Way can now be found. So, Howard Shapley first showed this in 1917 by looking at the distance of globular clusters using these variable stars. Right. So, by assuming the most distant globular clusters would lie outside the Milky Way, he found the extent of the Milky Way's halo. All right, so there's a globular cluster. Globular clusters tend to be a dense collection of older stars. All right, so this is basically globular cluster M4, globular cluster M3. Right? This would be pretty dense. Right? Here's a galaxy cluster. You can see they're way the heck out there in the halo of the Milky Way. Right? So that's basically tells us the extent of our galaxy. The main part of the galaxy is actually basically here in the disk and the central bulge. And out to between the sun and the center of the galaxy is about 8 kiloparsecs, about 24,000 light years. Okay, so the structure of the galaxy consists of several parts now. All right, there's the galactic disk, which we talked about, the galactic bulge, we talked about a little bit too, the galactic halo, which we just discovered by looking at the galactic clusters, and the galactic center, which we will talk about toward the end. All right, so the galactic disk is home to most of the young stars in the galaxy. The galactic bulge consists mainly of older stars. The galactic halo is just that, it's a halo, right? Mainly old stars, it's home to many galaxy clusters, right? And the galactic center contains a supermassive black hole, which we'll talk about near the end. All right. So let's talk about some of the structures of these things. So the structure is the halo, the disk, and the central bulge. That's the main part of the galaxy. The diameter of the disk is about 100,000 light years, about 30 kiloparsecs or so. The spiral arms are in the disk, outside the bulge. Right, near all the gas and dust, and all the new stars are in the disk and the bulge. The disk rotates about the galactic center. Stars close to the central bulge move faster than stars farther away. And the sun sits at 8,000 parsecs or 8 kpc from this galactic center, and moves around once every 225 million years. Right. So let's talk a little about basically kinds of stars that we have. So the kinds of stars we have in the galaxy are basically two kinds, old stars and new stars, right? So stars that form basically when the galaxy formed are called population 2 stars. They're mainly hydrogen and helium, fewer heavier elements, all right, because previously they had not been processed so much by other stars, and so they don't contain what we call a lot of metals like carbon, oxygen, all the other stuff, anything heavier than hydrogen and helium. And they land all parts of the galaxy, the halo, the disk, and the bulge, right? But primarily they make up the bulk of the bulge and quite a bit of the halo. Younger stars are formed matter in the disk of the galaxy, are called population 1 stars. They're made from processed materials that have been processed through stars already. So matter that was once in stars that would have died and basically been blown out and redistributed throughout the entire galaxy. So they had to have like much more carbon and nitrogen, what astronomers call metals, basically, iron, for instance. So so they consist of basically stuff that's been reprocessed. And so population stars are younger and begin to rise with a larger fraction of heavier elements than population 2 stars. Okay, so however, they're both mainly made up of hydrogen and helium, right? And even population 1 stars, like the sun, heavy elements are just a small fraction of the total mass. So galactic clusters form roughly about the same time as the galaxy form. They're all dense clusters with up to about a million stars or 10 to 6 stars, and all of them are population 2, right? So they don't really are formed or reformed basically from material that's been recycled, right? Here's an example of prototypical galactic cluster, M3, right? And galactic clusters typically are among the oldest objects in the universe, right? So now, the question might say, we've been talking about Milky Way being a spiral galaxy. So how do we know the Milky Way is a spiral? All right, well, there are several ways, right? So the easy way is to look at the gas, right? So if you have cold hydrogen gas, it emits radio waves with a wavelength of 21 centimeters. This is called 21 centimeter radiation. It's one of the most interesting ways of defining hydrogen in the universe, which is basically ubiquitous. And what happens is that basically, if you're looking at different parts of the galaxy, right, and it's rotating around, you're going to see different Doppler shifts, right, from that 21 centimeter radio wave, right. So basically, each one of them would belong to a different arm and will have a different velocity associated with them. Okay. So from Newton's law of gravity, one can find the mass of a galaxy inside orbiting star cluster from basically period orbit. Okay. So the mass of the galactic galaxies was found this way to be about 200 billion solar masses. All right. So that's good. All right. So you can figure out how massive the disk of the galaxy is. But then as you look at orbits of galactic clusters and gas clouds that are further away from the center of the galaxy, something strange happens. Right. The matter does not does not end with the edge of the disk, but keeps on going. All right, so there's actually some stuff out there which is not from this and not from the bulge. All right, so this is what's called the rotation curve of a galaxy. You can measure basically how fast a galaxy moves as a function of basically distance from the galactic center. Right, so you move further and further away. Right, you should end up seeing rotation speeds if basically the mass that we see is basically all in stars or gas and stuff. Then what we see is the rotation rate actually going down. But in fact, it doesn't. It stays flat. So this is what's called a flat rotation curve, right? And what that means is that basically that it can't just be all the mass cannot just be just what we see. It has to be stuff that we do not see as well, right? So the speed at which galaxy clusters orbit the galaxy imply a much larger mass than what is seen. And so basically this mass is called dark matter, right? Matter that's too dim to be seen, lies in a halo and the rest of the galaxy. And most of the galaxy mass actually is dark matter. And we do not yet know what this dark matter exactly is, right? But this is true of all large galaxies whose masses we've measured. Pretty much every galaxy we see out there has basically some measurable amount of dark matter, which consists mainly of the main part of that galaxy. Okay, so let's just summarize the dark matter just a little bit. All right, so how fast the galaxy orbits, how fast the star orbits the galaxy tells you how much mass there is inside the star's orbit. Faster the star moves, the more mass there must be. Stars far from the galaxy move unexpectedly fast, and therefore there must be more mass in the galaxy than we can see. And so 90% of the galaxy mass actually is this dark matter. Matter is too dim to be seen. All right, we sort of know where it is, all right, but we don't know what it is yet. All right. Now, I also mentioned basically there's a supermassive black hole at the center of the Milky Way, right? So, how do we know this? Well, first of all, the Milky Way, the center of the Milky Way is a very bright radio source. If you look in the radio telescopes, the Milky Way's center really stands out, right? And the center of the Milky Way is in the direction of the constellation Sagittarius, and because of the brightest radio, because the galactic center is the brightest radio source of Sagittarius, the source is named Sagittarius A, right? So was not really clear what provided the radio waves for a long time, and it was this day of 50 years. And basically, what it is basically a black hole, right? So people have observed the center of Milky Way actually for 20 years now at this point, and so they've been basically find strong evidence that there's a black hole there. And how do we know that? Well, if you look in the infrared, you can see stars orbiting this galactic center, right? So by observing how these stars orbit, you can tell basically there are about 4 million solar masses that lie within 6 light hours of the center. So this is a lot of mass in a very small volume, right? And basically from the short time it takes them to complete their orbits, one can basically say that they're orbiting something whose mass is about 3.7 million times the mass of the sun. So this is basically squeezing something a few light days across, roughly the size of the solar system. So this basically strongly says there's a 4 million solar mass black hole in the center of a galaxy, right? So here's basically what the orbits look like. So this is 10 years of data. This is back since 2012. Actually, there's more data now, right? But what's interesting about 2012-ish or so was that this star right here, let me see if I can get this mouse back. Yep, this star right here called SO2. Okay, SO2 complete orbit, right? So they've been observing this thing, and they completed it. Some of these other stars, we've been observing them for a long time. They're still not completed their orbit yet. But by completing orbit, basically, you have much better constraints on the central system. So look, basically, if you look at it again, let me see, play again. This star, the SO2 is going to come really close, and as it comes really close, it moves very quickly. This is basically Kepler's third law, right? And so this is basically strong evidence that something is really massive and really dense in the center. Okay, so that's our galaxy. Let's talk about other galaxies now. So Immanuel Kant in 1700 wrote about these small nebulated patches in the sky. Now, it wasn't what clear with these patches. These are basically blobs, stuff in the sky. It wasn't really clear. Some astronomers thought they were just part of our galaxy. It's kind of like the Milky Way in some way. If you look at the night sky, the Milky Way is like some fuzzy thing up there. So maybe they're just part of our galaxy. We just don't see it. But others thought they were other galaxies. So this was called a Shapley debate, and they're after the two antagonists. So I think it was Hubble versus Shapley, right? And what happened was that in 1922, Edwin Hubble found a Cepheid in the Andromeda galaxy. So then, once he found the Cepheid, And this was mainly because Edwin Hubble had access to a big telescope at the time. So once he found the Cepheid, he was able to use the Cepheid to measure the distance to the Andromeda Galaxy, and it was much farther than any star known at the time, right? So this Andromeda was measured to be 2 million light years, much larger than the 100,000 light years size of our galaxy, right? So let's talk a little about types of galaxies, all right? So the Milky Way is what's called a spiral galaxy, and what distinguishes these galaxies is that they have features called spiral arms, and these are a beautiful picture of the Whirlpool galaxy with these beautiful spiral arms, right? And there are some spiral arms of various types. So for instance, this is a multiple arm spiral. This is a bar spiral. That's another bar spiral. This is a two arm spiral. This is a spiral seen edge on. And this is maybe a dwarf spiral. All right. So spiral galaxies have four components which we have to discuss for our galaxy. So first of all, they have a flat rotating disk of stars, now with spiral arms, and the spiral arms are the younger stars. They have a central bulge mainly of older stars. They have a halo of older stars around it. These contain galaxy clusters, and all of them, as far as we can tell, contain a supermassive black hole. The spiral arms appear brighter because they contain most of the young stars. However, they only have about 5% more stars than the rest of the disk. So for instance, if you look here, right, it looks bright, right? But if I tell you there's only 5% more stars, you might not believe me. But in fact, it's true. Okay. So here's basically a colorway view or a side view of a galaxy. There's a central bulge, there's 8 kiloparsecs away, there's the sun, there's our disk, pretty thin, there's galaxy cluster, and that's part of halo. Okay, the spiral structure can vary from galaxy to galaxy. So SA galaxies are weak spirals, so here's a weak spiral. SB is a visible spiral, and SC is a prominent spiral, right? So astronomers have great ways of naming things, right? A, B, and C, right? More than half of the spirals of all spirals have a central bar, as most half the galaxies what we call bar spirals. The galaxy, our galaxy, for instance, the Milky Way, has a weak bar. Okay, these bars can connect up the spiral arms, but not always. Right, so this is, for instance, NGC 1300. Okay, this is another one, Sculptor Galaxy. Again, you see the bar spiral right there, beautiful bar spiral. 3 more bar spiral galaxies, those beautiful bar spirals. Okay, so I've talked about all these spiral arms. What are spiral arms? Still not clear what drives the spiral arms that we see in spiral galaxies, right? But we at least do know that gravity plays an important role, right? So gravity causes things to clump up. But how gravity organizes things in the spiral arms is not clear yet, right? Now, there's one thing that we sort of do know, right? We do know that spiral arms are not material themselves in the spiral, right? So not like something set it up and it was a spiral. Because if it were, then what will happen is that if it's matter, it will start to wind up. And it'll wind up until it disappears. This is called a winding problem, right? So for instance, you take a spiral structure here, the inside will move faster than, let's say, the outside. And so basically it will complete more rotations than the outside. So you start winding everything up. And at some point, basically wind everything up to a perfectly flat disk. Don't see a spiral anymore, right? But we see lots of spirals. That can't be true. All right. So here's animation of that winding problem. You see that basically I'm producing more and more winds. At some point, basically, it's going to look something like a disk, right? From far, far away. Okay, so what are they then? So here are a few ideas. So the first thing, spiral arms are what's called spiral density waves. So not material, but the pattern instead. Matter flows in and out of spiral arms. So for instance, basically, here's a spiral arm. As things come through, basically it gets compressed. It forms a bunch of stars. And as it does, basically the stars leach out, right? And basically it keeps going on, right? So basically you have just essentially material comes in, forms some stars, comes back out again. And the forming stars produce bright young stars, which makes the spiral arms stand out. Okay. So it's basically in a lot of ways like a traffic jam, right? Traffic jam is not a physical thing, it's really a pattern, right? Because all the cars are essentially still moving in principle, right? So what happens is like if you look at a traffic jam, right? Whoops. If you look at a traffic jam from a bird's eye view, basically you see cars pile in, cars leaving, for instance. Now, you always say that there's a traffic jam here, right? But that doesn't mean traffic jam is made up of cars that are stalled there, right? Because the traffic jam isn't moving anywhere, right? So these cars are moving, these cars are moving into it. But what's happening is a pattern, right? So cars are coming in, they're slowing down, they're jamming up, and then once they pass the big yellow truck, they can go free again, and they're going faster again. It's the same material does not always make up the traffic jam, but the traffic jam will stay in the same place. Right? If we apply this pattern to that, we can basically produce the same thing. You can see here, if you're eagle eye about it, there's stuff coming in, stuff coming out. Let me see if I can get this thing up. There we go. There's stuff coming in, stuff coming out, and so this pattern basically stays put. I can put my pointer there. It's not moving, right? Right, but yet the stars itself are, right? So it's a pattern that's been set up in such a way that you can see something that looks like a pattern, but in fact is actually is not made of material. Okay, there's another idea. The other idea is that these spiral arms are known to be formation sites of young stars. And so what it is basically self-propagating star formation. So stars form waves, so basically have some gas, they form into young stars. Basically, these stars explode or something like that, and compressing the gas, and that compressed gas basically makes new stars. And so basically, you have this like almost like a dynamite sort of thing going down, which lights up the galaxy. All right. Okay, so that's one kind of galaxy, spiral galaxies. The other kind of galaxy are called elliptical galaxies, and these are generally the largest galaxies in the universe. So here's basically a picture of the Virgo cluster, which is a collection of large galaxies. And there's a big elliptical in the center and lots of little ellipticals around. So each one of these little ellipticals are far larger than our Milky Way, and the big elliptical is many, 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 many times larger than our Milky Way. Okay. Now, this classification of spirals and ellipticals goes way, 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 way back. So in the 1920s, shortly after Hubble discovered there were many galaxies in the universe, he went about starting to classify them. At the time, he knew of spirals and ellipticals, but he had various degrees of structure. So this is when Hubble's classification scheme. There's ellipticals and there are spirals, and the spirals are broken into two types: regular spirals and bar spirals. Right? Okay. So this is known as a Hubble tuning fork. Right? It's still used today. I mean, it's not doesn't. The problem is that it doesn't depict anything evolutionary. It's like you can't really say basically how these spirals become these spirals or become these ellipticals. All right, now there's one more classic galaxies that Hubble didn't know about in the nearby universe. These are what's called regular galaxies because they have no regular shape associated with them. They're usually small galaxies with lots of dust and gas. So here's the three types of nearby, mainly old galaxies: ellipticals, the little gas or dust there. There's no new stars, wide range of sizes, but mainly the bigger ones. Spirals, gas and dust in the nucleus, and disk in the nucleus. New stars are always forming in spiral arms. That's the majority of star formation there. And they're about medium-sized ish or so. So we're roughly the size of the Milky Way. And then we have regulars. Gas and dust throughout. All right. There's new stars throughout, and they tend to be smaller. Okay, so there's a little galaxy, which is orbiting another galaxy. Okay. So new stars form from gas and dust in the spirals and elliptical galaxies. All right, spirals have both old and new stars, stars that form when the galaxy first formed, and stars that formed more recently. In spiral galaxies, spirals appear far brighter than the rest of this because most of the youngest, brightest stars are in the spiral arms. Right? So only 5% more stars are found in the spiral arms, but those 5% stars are the ones that matter because they are the ones that are the brightest. Elliptical galaxies are much older. They have very little gas and dust, look like basically what's called giant globular clusters. The stars of the galaxy formed when the galaxy formed. Elliptical galaxies are redder than spirals or regulars because they're new stars, and therefore you have new blue main sequence stars. And galaxies age slowly. They only appear in universe after billions of years. Okay. Now, let's talk a little about basically how galaxies move, right? So starting in 1914, Sipler found that galaxies outside the local group were all moving away from us. And Hubble started measuring distance using Cepheus. He and Hugh Mason found that speed would always increase distance to the galaxy. Right. So the way you measure velocity is by measuring the redshift or blue shift absorption line. So there's an absorption line here, and as you shift over, so you say, okay, well, why is that shift over? And well, that tells you because this galaxy is moving away, and you can also measure the galaxy using Cepheid variables, and you determine this distance is 17 megaparsecs away. Right. On the other hand, basically this is a bigger shift. This is for something much further away, 210 megaparsecs. Okay. So now when you plot it up, what you find is that basically as the distance to the galaxy increases, the velocity which they move away from us also increases. All right. So this is called Hubble's law right there. Right. So galaxies outside the local cluster are moving away from us. Their speed increases the distance from us according to Hubble's law. So the velocity is equal to a, which is Hubble's constant, which we will take for 70 kilometers per second. 70 kilometers per second, right? Still a really, really good number. Times d. D is the distance in megaparsecs. Right. So v equals h times d is called Hubble's law, and h is called the Hubble's constant. So to determine it, you need to measure the velocity of a bunch of galaxies at their distance. And to measure distance, we use Cepheid variables, which we talked about earlier. Okay, so current value Hubble's constant is really use Cepheid. Basically measures distance to the Virgo cluster and other galaxies within about 100 million light years of us, roughly about 30 megaparsecs. So basically one of the leaders in this area is Wendy Friedman. She's down at the University of Chicago now. She led the Hubble Space Telescope project from 1992 to 98 to measure the Hubble's constant. Okay, so once we figure out Hubble's constant, we can use the measure velocity of this galaxy, and if we can use the velocity of this galaxy, which is easy to measure from the spectral lines to get their distance. All right, so now it's distance is complete. We measure everything at the edge of the universe. And there it is. There we go. Cepheid, boom. Now we get basically Hubble's law, get the rest. We're done. Okay, so let's do a few examples of this, right? Of using Hubble's law. And let me get some paper here, and we'll switch over to our thing. Okay, so I might have to get a pen for a second. Let me see. I think I'm prepared, unfortunately, for this operation. Unfortunately, I do have a pen. All right, so let's escape out of this thing here, and let's go here, and we will turn on our capture device. I'll turn the screen capture off for now. Okay, beautiful. Okay, so let's do the first thing. Okay, let me make sure the focus is perfect here. Okay, there's my focus. I gotta lock my autofocus now. Put that there. Now we lock it. Okay, now it's locked. Okay, so let's talk about Hubble's law. I'll turn back my screen capture on now, and I'll turn this off first. Okay, now it's the first one. Galaxy is 100 megaparsecs away. How fast is it moving away from us? Okay, so let's basically do this now. Okay, so I'll do it vertically this time. Oh no, horizontally is better. Okay, okay, so galaxy. So let's write down Hubble's law first. Right, I'm gonna copy it. So V is equal to H times D. So H is 70 kilometers per second per megaparsec. I'll write it as 1 over MPC. Okay? And then D is in megaparsecs and V is in kilometers per second. So this is in MPC and this is in kilometers per second. Okay, beautiful. Okay, so now we said the first one is about 100 megaparsecs away. So 1. So D is equal to 100 megaparsecs away. Okay, how fast is it moving away from us, right? So this is pretty simple, right? So write down the equation. V is equal to H times D. Okay, I'll do it vertically just to save some space. And then this is equal to 70. That's Hubble's constant. D is in megaparsecs, so that's 100. Okay, so that's 7,000. Right? Okay, and the units are basically now kilometers per second. Beautiful. Okay, so that's the first one. Now the next one is that the galaxy D is equal to 2,000 megaparsecs away. Right? How fast is it moving away from us? All right, we do the same thing. V is equal to H times D. Okay, that's 70. That's 2,000. Now this is going to be 140,000. Hopefully I did that right. Kilometers per second. Right? This happens to be close to half the speed of light now at this point. Okay. Next one. All right. Number 3. Okay, so now this is actually the more relevant one. Okay, because it's easy to measure velocities. It's really much harder to measure distances. So the velocity of the galaxy. is okay. So I'll read it. I'll actually read it first, and then I'll do it again. So turn this off. So a galaxy is 2,000 megaparsecs. So, sorry, a galaxy is moving at 700 kilometers per hour away from us. How far away is it? Okay, so now let's do that one now. Let's do the screen capture, video capture again. All right, there we go. So for me, I will see it. So the velocity is 700 kilometers per second. Okay, and need to find d. Okay, so now let's write that down. V is equal to hd. Okay, so this is equal to 700 is equal to h 70 times d, which I don't know. So that means that d is equal to 700 over 70. That's 10 megaparsecs. All right. Okay. Now number 4. All right. Okay. So let's apologize for moving back and forth, but that's the only way to do this. A galaxy is moving at 21,000 kilometers away from 21,000 kilometers per second away from us. How far away is it? Okay, so now let's do the last one. Turn back on my video capture, and here we go. Okay, so a galaxy is moving. V is equal to 21,000 kilometers per second. So V is equal to hd. Now again, this is 21,000 is equal to 70, right? Times d, which is I don't know. So d is equal to 21,000 divided by 70. All right. So that's 100, right? So that's about 300 megaparsecs. Okay. And that's it. All right. So now turn off video capture, back to the screen, and back with our lesson. Here we go. There we go. Next one. Okay. Collections of galaxies. So most galaxies are not alone, but live in large collections known as galaxy groups or galaxy clusters. Groups can consist of basically tens of galaxies. Clusters are larger and consist of basically thousands of galaxies. All right. So the Milky Way lives in a small group with the Andromeda galaxy. So there's Milky Way, there's Andromeda M31, right? And this little group here with all the dwarf galaxies surrounding us is called a local group. Here's a 3D map of the local group. There's Andromeda there. There's M33, Whirlpool Galaxy. And here's a galaxy cluster. Each one of these galaxies is part of that cluster. It's crazy. Okay, another cluster. Hercules cluster, 500 megalight. Okay, so galaxy clusters are so massive they actually is gravitational lenses. All right, so this is basically a little schematic how that works. Basically, you have some light from some distant source. And what happens is that basically it comes around a gravitational potential well, let's say a galaxy for instance, and basically gets concentrated at the end right there. Okay, and so there's a few examples. These are galactic. These are galaxies acts gravitational lenses. So these are the galaxies here. All right, and you see basically the magnified images of these in the back. And every now and then, like for instance this one, right, or this one is a much better one, the alignment is so perfect that it almost gives a perfectly circular arc. Okay, it's called Einstein ring. So this is a perfect example of Einstein, near perfect example of Einstein ring. Here's another good example of Einstein ring as well. Okay, so you can actually do this with, if you have a wine glass and you're kind of bored, basically, right? You have a candle, which is a distant point source, right? You can basically tilt that wine glass. You see basically 1, 2, 3, 4 images, right? Images always come in pairs, it turns out, unless you have something which is a perfect ring. And there we go, it's a perfect ring. Okay, so there's also gravitational lensing by clusters. So they're so massive that distort the image of the galaxies behind us. This is a big cluster, and these are all many different galaxies behind us. That's one galaxy right there, another galaxy, another galaxy. So these are all lens galaxies against this background cluster able 2218. Okay, now galaxies are made of large collections of stars. So you might expect that if you break up the light, that most of the light will be starlight, and most of starlight is visible, right? So we expect there to see their spectrum to peak in the visible. So this is true of most galaxies, but not all of them, right? So some of them actually show some non-stellar radiation or spectrum, and because they are so bright, they're typically called active galaxies. So if it's a normal galaxy, there's the peak in the visible, and here's active galaxies. There's stuff in the radio, stuff in X-ray. Basically, if anything, there's actually a dip actually in the visible light. So you might wonder how that happens, right? So it turns out active galaxies are far more luminous than normal galaxies and have non-stellar spectra, emitting most of the source outside the visible part of the electromagnetic spectrum. So Seyfert looks like a normal star, except that Seyfert has an extremely bright central galactic nucleus, right? So the rapid variability, the rapid timescale on which it changes, implies the source radiation is very small, less than 1 light year across, right? Okay, so here's a Seyfert galaxy. It looks kind of like a normal spiral, but in the center, the very, very bright galactic nucleus. This is a picture of Circinus galaxy, right? And they vary by quite a bit. So this is intensity. Over a period of years, they vary quite rapidly, right? You don't see this in normal galaxies because the stars live right tens of tens of billions of years, and so basically it's just flat, right? But here it's varying on a year by year basis, and so in order to have that happen, the source cannot be can be larger than a few light years across. Okay, so other types got very strongly radio, but the radio doesn't come from the central source, but usually two giant lobes extend from it. Okay, so for instance, this is the Centaurus A. This is a hybrid image. This is a visible image of it, and what they superimpose on it is the radio image of it. Right, and the radio image of it basically looks nothing like a big circular ball with dust laying there, right? Rather, it looks like these giant lobes basically out there. So that's basically the main source of radio, secondary source of radio there. So these are called radio galaxies, right? So they have a huge amount of energy in the radio part spectrum, and the corresponding visible galaxy, usually elliptical galaxy, kind of like this one. It's kind of almost like elliptical-ish, right? It's M87 actually, which basically made the news recently because this is the galaxy they imaged a black hole of. Right, so these radio lobes are powered by a powerful radio jet which is the center of the galaxy. When it slams in the galactic medium, it blows a bubble and becomes a radio lobe. Right, so basically this is a computer simulation which I did myself many years ago. It's like a jet that's plowing through the intergalactic medium and basically just spewing out all this material, right? And all the shock material behind it. Let me see, get this mouse going. All the shock material behind it is very, very high temperature, and because of that, it will emit very strongly in the radio. Okay. So now what happens is that some of these strongest radio sources seem to be identified with very funny looking stars, which look nothing like galaxies, right? Okay, but they're not quite stars either, so they were called quasi-stellar objects, or quasars for short, because they kind of look like stars. Right, there's a quasar, right? Big, round, doesn't really see, it looks point-like, doesn't really say much. There's another quasar right there, right? Looks like a star, right? It's not like a galaxy, it doesn't have a big structure. So for a long time, it wasn't clear how far away these quasars were until they finally identified a spectrum of one of these things, and would show hydrogen redshift by 15%. So from Hubble law, you can figure out how far away it is, and the answer is really far away. Okay, so basically 15% speed of light is about 48,000 kilometers per second, and so this thing was about 642 megaparsecs away, or almost 2 billion light years away. So this is very, very, very far. Okay, now these quasars are in fact galaxies. They're so bright, the central source is so bright that it obscures everything else. You don't see anything else because the central source is just so bright. Okay, that's why they look like stars. They emit 1,000 times more energy than normal galaxies. All right, and because it's so bright, you cannot see the host galaxies for a long time. And so these, but with Hubble, you can find they're kind of there. It is. There's in fact the galaxy here. Generally, these quasars are not just single galaxies, but multiple galaxies, and they might be formed from the fact that basically two galaxies are colliding with each other. Right. So, what powers these active galaxies, Seyfert galaxies and the quasars? So, the power source of the active galaxies must be phenomenal. They are bright. They're going to be much brighter than normal by a factor of 1 million to 100 million. Right. They're compact. they vary on very short time scales, 1 week to 1 year time scale. So at most, it can be basically about 1 light week or 1 light year in size. And spectral lines are going to show evidence of motion of 10,000 kilometers a second. So the only power source matching all these things is a supermassive black hole. Right. So active galaxies show two component spectrum. There's a narrow component and a broad component. Right. So basically, if you look at a narrow galaxy, you normally see there's a broad component here, and sometimes there are these narrow lines. Right. And we might wonder where these are from. And it's generally thought that basically a supermassive black hole accretes gas from a disk, right? And this is what the secretion of gas is what powers these active galaxies, right? Also, basically, galaxies use to shoot jets of particles away, which is what's observed in some of these radio galaxies as well. Right, here's a zoom in of such a picture of the active galaxy. There it is. There's my jet. There's the intertwining magnetic fields, which help push out the very, very large distances. There's the inner region of the accretion disk, all right, where you see it's very bright. And occasionally, basically, some burps and wallops, which sends out material out of the galaxy, right? Okay, so we might ask why black holes? Why not just a bunch of stars, right? Well, these active galaxies have to be extremely luminous, so you have to need extremely efficient power source. So black holes turns out the most efficient way of generating energy in the universe, right? And that's because black holes convert 10% of the rest mass of stuff falling into energy, compared to hydrogen fusion, which converts at most 0.7%. They're also very compact. Most of the light is made close to the black hole, where light size is basically a few light seconds or maybe 1 light minute across. And stuff orbits around black hole really fast, right? So it explains why we see evidence for rapid motion. Okay. We don't always see this motion, right? So basically, sometimes you only see these what's called these narrow lines. So to explain this, astronomers think there is basically a dusty donut around these objects. So for instance, like you don't always see this bright source in it. Sometimes you see these like you see something that looks kind of bright and like, you're not sure why. Well, that's because you're looking at it from different angles. So if you look on the top of this thing, you see the bright central engine, you see the jet, blah blah blah, and this thing looks really bright. You look from the side, basically, you're obscured by this huge dust torus, basically, and because this dust torus is in the way, you basically see a lot less, right? So from certain angles, you see the central accretion disk. Other angles, you do not. You only see basically the narrow lines of these objects, right? So there's some surprising evidence that in fact this is a correct picture. So it turns out that if you look at the same galaxy from multiple angles, you can test this idea. So you might ask, how do you look at the same galaxy from multiple angles? It's kind of hard, right? So it turns out if you look in scatter light. So for instance, if you're seeing here and you get some light that's scattered, so reflected into your line of sight, if you look at basically scatter light, you might see some evidence that in fact it looks different from a different angle, and in fact this is in fact true, right? So for instance, the system Markarian 348, you look at a scattered light, the broad line becomes very bright. So there's a scatter light, there's a broad line, all right? So it's coming from a different line of sight. So this big broad region here is not visible here, but it's clearly obvious basically when you have to look at a scatter light. Okay, so active galaxies are really the same beast, all right? By looking at different angles, like for instance, like here you might see a C1, on this side you might see a C2, on this side you might see a really quiet quasar, right? Other times you might see quasars, for instance, or you might look from the side, you might see a narrow line radio galaxy. Okay, and that's it for galaxies.